So in the previous video, we learned about polar bonds, all right, which are covalent bonds where you have two atoms that don't share the electrons equally, all right? One of them has a higher electronegativity, which is its ability to pull electrons towards itself. And what we discussed earlier is that that creates a slightly positive and a slightly negative end to that bond, all right? So in this video, we're going to discuss what effect this has on overall molecules, not just isolated bonds, but like if it's part of a larger molecule, for example, what would that do to the overall molecule? All right. So you might conclude that like if you have any polar bonds in a molecule, that might make the entire molecule polar. All right. And if it's a very small molecule, a lot of times that is the case. For example, if you've got HCl, it's the entire molecule is just one covalent bond, all right, between two atoms, all right? And so it's very easy to see in this situation where this delta negative at this end of the bond would cause this entire side of the molecule to be delta negative, all right? This side is delta positive, all right? However, it's not that easy to define something as being polar because there's actually a way that molecules can have polar bonds within them, but the overall molecule is not polar, right? And that situation is going to happen whenever you have polar bonds, but those polar bonds either pull away from each other in exactly opposite directions or push towards each other in exactly opposite directions, all right? And when I say exactly opposite, it doesn't just happen to be like two things. It could be, for example, if you had, imagine a ball here, and you had a rope and you pulled on it that way, and this way. All right. All of these forces would cancel out. All right. So even though it's a lot easier to see when things cancel out when you're pulling 180 degrees opposite, but you can do the same canceling out of forces when you do a situation like this as well. All right, so the classic example of this is carbon dioxide. All right, so carbon dioxide, if you go back to VSEPR theory and you were to try to determine, all right, well, what shape would this have? All right, well, there's two clouds, all right, and there's an atom at the end of each of those, and if you use the chart, you can figure out that would be linear triatomic. All right, so this would be a 180 degree angle right here. You've got electrons being pulled more towards the oxygen. So if we, I've copied some of the numbers, common electronegativity numbers, and put them here. All right, carbon is 2.5, so we could say 2.5. Oxygen is 3.5. And if you calculated that difference in electronegativity, it would be 1.0. And that is in that range where this would be considered a polar bond. All right, so this bond gets pulled that way, and the electrons in this bond get pulled the exact opposite way. All right, so since the pulling exactly cancels each other out, there isn't one positive end and negative end to this entire molecule. All right, therefore, this molecule is considered nonpolar. All right, even though it contains polar bonds. All right, let's contrast that with water. All right, remember the shape of water is going to be like this here. All right, it's going to be, water is a bent triatomic molecule. It's got 4 clouds, but only 2 of them are connected to atoms. All right, so it's got this bent shape, but these oxygen-hydrogen bonds are polar. All right, that's a 3.5 and a 2.1. So the difference between those is 1.4. All right, that's enough to be considered polar. So these get pulled in this direction, these get pulled in that direction. And one way to think about this is to think, all right, what if these were ropes? And I pulled in the direction that the arrow is going. Would that cause this thing to move? And hopefully you could see that overall this would want to get pulled downward if people pulled in those directions. All right. Whereas here, if people pulled in exactly 180 degree opposite directions, there would be no way that the central atom got pulled. All right. So, so overall, the bottom part of this molecule, oops, I made a mistake here. All right. So correction on this one. The oxygen is more electronegative, so it's going to be pulling the electrons in these directions. All right. And if you were to do that, you would recognize that the top half of a water molecule has more electron. Essentially, the electrons are going to spend a little bit more time on this top half than they would on this bottom half down here. So this part right here would be slightly delta negative, this would be slightly delta positive, and this would cause this molecule to be considered polar or a dipole. All right. So in summary, there are two different ways that a molecule can be considered nonpolar. The first way is that it contains only nonpolar bonds. All right. So for example, if I were to show this molecule right here, all right, and its shape would be bent triatomic. Right. Well, we just saw an example of a bent triatomic molecule, which is polar. All right. And that's because it contains these polar bonds that go in that direction. All right. But here, take a look at the electronegativity difference. It's only 0.4. All right. So even though there's a slight difference in the electronegativities, it's not big enough to be considered polar. All right. So one way to think about this is, essentially, if there's absolutely no pushing or pulling going on of the electrons in any of the bonds, it's impossible for there to be a polar, a slightly negative or a slightly positive side. All right. The other way that you can have a nonpolar molecule is if you have polar bonds, but they exactly cancel each other out. All right. And carbon dioxide is a classic example. But also take a look at this molecule right here. All right, these would be polar bonds between the boron and the bromine. All right, but because of the shape, which is trigonal planar, the pushing and the pulling would exactly cancel each other out. All right, so let's practice this with a couple of molecules here. All right, let's pretend that we had CH3Br, this molecule here, and this molecule here. They're very similar. So they would all be, I'll go ahead and mention that they would all be tetrahedral molecules if you do the Lewis structure. So I've drawn them in the following ways. All right, for this molecule, I've put the hydrogens at the bottom. Picture these bottom atoms as being like the legs of a tripod. All right, and so this one is going to come slightly towards you. This one's, to the right and slightly back away from you. This one's exactly going out to the left. All right. The bromine would be sticking straight up. Okay. Well, these bonds, if you look at the carbon-hydrogen bond, all right, 2.5, 2.1, these down here, all these bonds down here are considered nonpolar. All right. But this bond right here, if you look at the difference between 2.8 and 2.5, that's also nonpolar. All right. So if there are no polar bonds anywhere in that molecule, it's impossible for the overall molecule to be polar. All right. So this guy is nonpolar. By virtue of the fact that it contains no polar bonds. All right, let's take a look at this molecule right here. All right, again, the same thing in the bottom. These are all carbon-hydrogen bonds. They're not going to be polar, but between carbon and fluorine, 4.0 and 2.5, that is a delta electronegativity of 1.5. That makes this a polar bond. All right, the fluorine is going to want to pull those electrons towards it. All right. And so if there was no pushing or pulling at all down here on the legs of the tripod, but there was pulling in this direction, that's a lopsided amount of electron pulling. All right. The top part of this molecule would be delta negative. All right. So this is a polar molecule. And the reason that it's polar is because it has asymmetrical polar bonds. Okay, so it's got a polar bond, but they don't get canceled out. There is an overall direction that they get pulled. All right, and the last example is this one here. And this is a tetrahedral molecule, and all of these are polar. All right, and if this was a tetrahedral molecule, all right, if you pulled in all these different directions, all right, you would notice that the central atom would not want to move. All right, if you took this molecule, had it in outer space, and you had 4 different people pulling on the fluorines in the direction that they're going, this central carbon would stay exactly where it is. Those forces would cancel out. All right, so this would be nonpolar because of symmetrical polar bonds.